Hi, I'm going to talk you through how to solve these problems very quickly. So hopefully you're having some success with it. But if not, maybe these hints will help you out. The problems on the the problems on the retake for the test, basically exactly the same as this. A little bit, just a little bit changed, but the basic strategy is exactly the same. So hopefully this will help. So I'm just going to run right through it real quick. So this is how I would attack the problems. Okay, the first question says, a truck is moving along at 25 meters per second when its brakes fail and it coasts up a hill that gives it an acceleration of negative 1.2 meters per second per second. This, of course, is supposed to say sorry about that, how far does it make it up the hill after 10 seconds? Okay, and so if it makes it better for you, you can go ahead and draw a picture. So you've got a truck here. That's my simple truck. It has some initial velocity, but it is experiencing an acceleration downwards. So there's the initial velocity, and the acceleration is going in the opposite direction there. I don't know if that helps you for this. The question then is, how far does it make it up? So it's trying to figure out how far up the hill it makes it. Okay, so let me identify the things that I know. First off, this guy right there is an initial velocity. Okay, this guy right here is an acceleration. This guy right here is a time, of course. And what it's asking you for is how far. And how far, of course, talks about delta x, the displacement. And so I'm looking for a formula that has delta x and the initial velocity and an acceleration and a time. And so hopefully you're starting to think, well, maybe that sounds like the master motion equation, which was 2.4 on our formula sheet. It says delta x equals the initial velocity times the time plus 1/2 times the acceleration times the time squared. And so you really just plug straight in, and at the end you should end up with a displacement that gives us this positive 190 meters right there. Hopefully that makes sense to you. It's pretty straightforward. You've got the time, you're just looking for the displacement, and the motion is accelerated. So anytime you have those three things, you're really looking at this master motion equation, which is 2.4, I think, on the formula sheet. Okay, I'm going to let you try to solve that for yourself, but at least that gives you a hint. Okay, take a look at B. So we've got a situation where a cannon, and I'm just going to draw it like it was firing horizontally here, because it really doesn't matter. Okay, and so the cannonball's inside, and later on the cannonball emerges here from the edge of it and has some velocity right there. And we know that velocity is 1,000 meters per second. Initially, how fast is it going? It's not something that's actually said in the problem, but you can imagine that when you put the cannonball into the cannon, it doesn't have any velocity. And so until you fire it, it's not going to have any velocity. And so it's implied, although it's not said, that the initial velocity is 0. So it's important to remember there. Now you know it experiences an acceleration from here to there, but it doesn't tell you in the problem what that acceleration is, and so you can't really address that. It does tell you, however, that it moves a distance, that's your delta x, of 0.7500 meters. And it doesn't really tell you anything else other than the fact that it wants the time that it was accelerated. So we're looking for a delta t here. There we go. We don't know that. So here's the problem. Does it have anything to do with acceleration? We know that the ball is accelerated, but we don't know what that acceleration is, and we're not even asked to find it. And so that eliminates of the formulas that we have. We've got 5 for this unit right here. And this one, and that one all have accelerations in them, so we can't use those. And so we're left with just these two. And they're both equal to the average speed. And so what we can do as we've done in the past here, is set those two equal to each other, and that makes them much more flexible. And so what it looks like is this. So the first 2.1 says the average speed is equal to the change in displacement over the change in time. That's nice to know because we have a displacement and we're looking for the time. And so this is a good one to use. We don't know what the average speed is, though. We know what the initial speed is, 0, and we know what the final speed is, 1,000. But we don't know what this average speed is, so we can't put anything in the left-hand side of the formula yet. We can solve this for delta t, which would be helpful, but we can't really do anything more with it yet. So we have to employ the second formula, 2.2, which tells us that the average speed is also equal to the initial speed plus the final speed divided by 2, just like any average formula. And so we set those two equal to each other. And again, we solve it for this guy right there. So when you do solve it for that, it should look like this. Delta t is equal to, let's see, delta t is equal to 2 delta x over v1 plus v2. Okay, so the v1 plus v2, that's 1,000. The 2 right there is going to help you out with that just a little bit. Kind of divide that out. And then the delta x is this 0.7500 meters. So hopefully that helps. I'm not going to, as I said before, I'm not going to solve it for you, but at least this gives you a place to try to attack it. Okay, last question. A cannonball is fired straight up. Now it's the same cannon in this case, right? So no big surprises here. So we've got the same cannon. That was a terrible job. Excuse me a minute while I erase this here. I can't, sometimes drawing on this thing is not so easy. That was not much better. Okay, so we have a cannonball right there. And the cannonball is being launched upward, so that by the time it leaves here, it has some velocity upward. Okay? Now, I'm going to draw this situation out over here. So let's imagine that it starts off, as it leaves the cannon at this level, it's going up, and going up, and going up, and going up, and going up, until finally it gets to the top, and we're actually trying to find what that height is, right? And then it starts coming back down again until finally it hits the ground. And so we're trying to find this delta y, this height that it gets to. Now we know a couple of things. First is we know that when it leaves the cannon, which again I drew super ugly. Sorry about that. Eesh. Drives me crazy there. There we go. When it leaves the cannon, it has this initial vertical velocity of 1,000 meters per second. We know that we're looking for the height, as I said just a minute ago. We know that the thing that is changing the speed is the gravitational acceleration, which is negative 9.81 meters per second per second. And we know one last thing, and it's kind of hidden in there, and that is the moment it gets to be at its highest point, that moment is when it stops going up and starts going down again. So that moment right there has a v2 of 0. And so we know the initial speed, we know the final speed, we know the acceleration, and we're looking for the displacement. Did you notice that there wasn't any time in there? And the fact that there wasn't any time listed is a pretty good indication that we want to try to use this 2.5 formula, which is the no time formula. v2 squared equals v1 squared plus 2a delta x. Now I'm going to change that up so that you can see what it looks like for this problem in particular. v2 is 0. v1 is 1,000, so I'm just going to leave v1 in there. You can add in the stuff later on. Plus 2 times little g times delta y, because we're talking about a vertical displacement. So if I solve that for delta y, it's going to look like this, right? So I'm going to subtract v1 squared from both sides. End up with v1 squared divided by 2 little g is equal to delta y. And that should get us the correct answer right there. So again, v1 squared, the opposite of v1 squared over 2g should get us the correct answer. That opposite sign, that negative sign right there, you might be worried about it, but remember that this down here at the bottom is a negative 9.81, that little g right there. So that negative here and the negative there make your answer positive on this side, which means your delta y is positive. And doesn't it make sense that the cannonball would be moving up and not down in this situation? So again, hopefully that helps. If you have any questions, go ahead and email me. I should be on email most of the night tonight. Have a happy Halloween.